Welcome students. Good morning to all of you. Today we will start our next lesson and it is very important lesson and the name of the lesson is coordination compounds. Students, in the chapter coordination compounds we will study Werner's observations. Werner made certain experiments. He prepared a number of coordination complexes, coordination compounds, and he was the first person who gave idea about their structure. So after that, we will study certain terms and definitions which are used while studying coordination compounds. And then we have to study the nomenclature of coordination compounds. This means that if we have got the name of a coordination compound, can we write its formula? And if some formula is given to us of some coordination complex, can we write the name correctly? So we have to learn this. This comes under nomenclature of coordination compounds. And after this, we have to study the various types of isomerism which occurs in coordination compounds. Coordination compounds, they show the phenomenon of structural and stereoisomerism. We have to study that in detail. Then we have to study the various theories which have been given, which have been proposed to explain the structure of these coordination complexes. There are three theories which we will study. One is Werner's theory, second is valence bond theory, and the third is crystal field theory. Apart from this, there are other two modern theories of coordination compounds. They are Legend field theory and molecular orbital theory. These theories are not in our syllabus. So we have to study three theories: Werner's theory along with its limitations. Then we have to study valence bond theory, and also we have to understand why this theory had to be replaced by crystal field theory. And after this, we have to study why different coordination compounds, they show different magnetic properties. That means the reason for magnetic properties in coordination compounds we have to study. Now, another thing which we have to study is the color of the coordination complexes. Okay, the reasons for different colors of coordination complexes. And after that, we have to study a special topic, metal carbonyls. Okay, in which the metal atom or metal ion, metal atom, it combines with various ligands called carbonyl ligands, that is CO, to form certain compounds which are known as metal carbonyls. And the main important thing in this which we have to learn is synergic bonding. So please remember, this synergic bonding in metal carbonyls is also a very important topic. Then we have to study the various applications and importance of coordination complexes in our day-to-day life. Now we will discuss about Werner's observations. You know what are complex compounds? What are coordination compounds? We are writing formulae of different chemical substances. Sometimes we come across with certain formulae which have got a part which is written in the square bracket. So this part of the formula represents a coordination entity, right? So the compounds which possess one or more coordination entity in their formulae, they are known as complex compounds. Now, students, it was Alfred Werner who was the first person to prepare a large number of such compounds called, now we call them as coordination compounds, and he was the first person to study the structure of such compounds, right? Now, in the coordination entity which we write in the square bracket, there is a metal atom or ion, and this metal atom or ion is transition metal atom or ion. Now why transition metal atoms or why transition elements they form coordination entities? The reason is, there are two reasons for this. One is they are small in size, and the second is they have got high ionic charge. Okay, so Werner prepared such compounds and formed an idea about the structure of such compounds. And after doing these experiments, he gave an idea that a metal atom, transition metal atom, in such compounds exercises two types of valencies. One is called primary valency and the second is called secondary valency. Till now, you have heard only about primary valency, right? If I ask you, students, what is the valency of chromium in chromium chloride, CrCl3? And if I ask you, what is the valency of cobalt in the compound CoCl2, that is cobalt chloride? If I ask you, what is the valency of palladium in palladium chloride, that is PdCl2, you will immediately tell me that the valency of chromium in chromium chloride is 3 and the valency of cobalt in cobalt chloride is 2. Similarly, the valency of palladium in palladium chloride is 2 because you have studied only primary valency or valency, which you call, right? And then, do you know, if we dissolve this chromium chloride in water, how many ions we will have? If we dissolve one molecule of chromium chloride, we will have one chromium cation and 3 chloride ions. And the total number of ions which will be produced from one molecule, these will be 4. And if we dissolve one molecule of cobalt chloride in water, what ions we will have? We will have one cobalt cation and 2 chloride ions. And the total number of ions which will be produced in the aqueous solution, it will be 3. And if we dissolve palladium chloride in water, we will have one palladium cation and 2 chloride ions. And the total number of ions which we will get after dissolving palladium chloride in water will be 3. All these species, as you see, they ionize when dissolved in water. And all these species, that is chloride ions, they are linked, they are bonded to the metal atoms, whether it is cobalt, whether it is chromium, whether it is palladium, by valencies called primary valencies. Thus we see that primary valencies, they get ionized when dissolved in water. They produce ions when dissolved in water. That is, primary valencies are ionizable. Now I will tell you that Werner prepared a number of compounds by using cobalt chloride and ammonia. He used CoCl3, cobalt chloride and ammonia, and he got 4 different type of compounds from the same raw materials. The first compound which he got had a yellow color. The second compound was purple in its color, and the third compound had a green color, and the fourth compound, it was violet in its color. Then he checked the molecular formulae of these compounds. The molecular formula of yellow compound was CoCl3.6 ammonia, and the molecular formula of purple compound was CoCl3 5 ammonia, and the molecular formula of green compound as well as violet compound was CoCl3 4 ammonia. He studied these compounds and he made 2 types of experiments. He dissolved each compound separately in water and studied its conductivity. And he also studied the presence and quantity of chloride ions which are present in the solutions. Okay. Now the first type of experiments which he did were the conductivity experiments. The conductivities of the aqueous solution of these compounds, which was studied separately, came out to be different. Now you know that conductivity of a solution, it depends upon the number of ions which are present in the solution. Thus he noticed that the number of ions in the solution of each compound might be different. Then how do we find out the presence of chloride ions, or if we have to quantitatively check how much chloride ions are present? We treat it with silver nitrate solution, AgNO3 solution, and the chloride ions, they form a white precipitate of silver chloride. So this is how we can quantitatively estimate the moles of chloride ions present in the solution. So he prepared solution of each compound which he got separately in water, and he added silver nitrate solution to each compound differently, and he observed that he got different number of moles of silver chloride from these solutions, and his results of precipitation of silver chloride, they matched with his conductivity experiments also. So the conductivity experiments as well as the amount of chloride ions in different solutions were matching. Now let us look at the formulae which were suggested for these compounds by Werner. He suggested these formulae on the basis of his above experiments, that is conductivity experiment and the experiment in which silver chloride was formed. Now for the first compound, yellow compound, he suggested this formula. You see, in square bracket he has written cobalt with 6 ammonia molecules, and outside the square bracket there are 3 chloride ions. This was the formula for yellow compound. And for the purple compound, he suggested this formula: COCl and 5 ammonia molecules in the square bracket and 2 chloride ions outside the square bracket. And for green compound as well as for violet compound, he suggested the formula COCl2 and 4 ammonia molecules inside the square bracket and 1 chloride ions outside the square bracket. Now you see, he has kept chloride ions, different number of chloride ions outside the square bracket in all these formulae. He kept that many chloride ions outside the square bracket that matched with his experiments, with his experimental results of conductivity and precipitation experiments. And the second point which you should note, that the formulae of compound number 3 and 4, they are same. The molecular formula of compound number 3, that is green compound, and the violet compound are same. He told that compound number 3 and 4, which have different colors, might be isomers. Now what are isomers? Isomers are compounds which possess the same molecular formula but they differ in their properties. So these two compounds, they possess the same molecular formula but differ in their color. Okay, so Werner gave a concept of secondary valencies. Werner told that chloride ions and ammonia molecules that are written inside the square bracket are bound to the metal atom, that is cobalt ion, right, by valencies which are known as secondary valencies. I am again repeating that he told that the chloride ions and the ammonia molecules which he has written inside the square bracket, they are bonded to the metal atom ion, that is cobalt cation, by valencies which he called secondary valencies. You will notice from the formulae of the compounds which were given by Werner, the total number of species whether they are ammonia molecules, whether they are chloride ions, which are present inside the square bracket, they are fixed. That means ammonia molecules and chloride ions, which he wrote in the square bracket, they are fixed in number, and that is 6. So what does it mean? It means that cobalt cation, it can bond 6 ligands, 6 such species only, and this is called coordination number of cobalt cation. It means that any metal cation, it has got a fixed number, that is called coordination number, that is the number of the ligands, that is the number of the species which can be attached to the central metal atom or ion. The anions, that is chloride ions, which are present outside the square bracket, they are called counter ions. The ions, chloride ions, which are present, which he wrote outside the square bracket, he told that they are bonded to the metal atom or ion by ionic bond. So when we dissolve these compounds in water, it is only these anions which become free, which ionize, whereas all the species which are written in the square bracket, they remain intact. Okay, so the anions, that is chloride ions, present outside the square bracket are bonded by ionic bond, so they only ionize when dissolved in water. Aqueous solution of such compounds do not give tests of species or ions which he wrote inside the square brackets. Okay, let's have a look. Now there I have given a table where I have written ions produced by these compounds in water are as follows. Now I have written the formula of the compound. Look, the formula of the first compound is cobalt with the 6 ammonia molecules inside the bracket and 3 chloride ions present outside the bracket. These ions which are present outside the bracket, they are known as counter ions. Now in the second formula, the second formula is formula of the second compound is COCl NH35. That means there are 6 species present inside the square bracket again. 5 are ammonia molecules and 1 is chloride ion. And outside the square bracket there are 2 chloride ions only. And in the third and fourth there is 1 cobalt atom, 2 species chloride ions, and 4 species, that is 4 ammonia molecules, they are present inside the square bracket. Now let us see, when we dissolve these compounds separately, when we dissolve each compound separately in water, how many ions are produced in the water. Now let us see, the first compound when dissolved in water, it will produce, one is the chloride ions, there will be 3 chloride ions, and then there will be a positively charged complex entity. So that means there will be 4 ions in total. One will be the cationic entity, complex entity, and 3 chloride ions. And let us see how many ions are produced when we dissolve the second compound in water. We get 1 positively charged coordination entity carrying +2 charge and 2 chloride ions. That means, what is the total number of ions which are produced? It is 3 ions. And in case of third and fourth compounds, let us see how many ions are produced in total. One is the coordination entity, positively charged coordination entity, and 1 chloride ion. So is the case in the fourth compound also. So what is the total number of ions which are produced in compound number 3? It is 2 ions. What is the total number of ions which are produced in compound number 4? Again it is 2 ions. That means only the ions species which are present and ions which are present outside the square bracket, they ionize in water, whereas all the species which are present inside the square bracket, they do not ionize. And if we test for these species present in the written in the inside bracket, they will not give any test. So they remain intact. So the metal atom or ion and various species which are present in the square bracket constitute a complex ion. So you understood? Primary valencies, they are ionizable. The counter ions which are present in the coordination compound, they ionize. They are free ions in the aqueous solution. Whereas the species which are written in the square bracket, they are bonded by secondary valencies, and on dissolving in water, they do not ionize.